Okay, thank you everyone for joining us for our next expert lecture. We're so excited to have you in our expert lecture here. I'll introduce Gwen Leiter, our CEO, to introduce Maxime.
Thank you, Nidhi, and thank you everyone who has joined us today for an incredibly exciting expert lecture. We are thrilled to welcome Maxime Gariel here today. And as you all know, GoAERO is focused on a singular mission of saving lives. We are sponsored by Boeing and NASA and RTX and a wide variety of phenomenal companies. So too, we are supported by our organizational partners around the world. In the coming month, you will see us at EAA's Oshkosh Air Venture, as well as AIAA's Aviation both in July. So we look forward to seeing you all there, should you be there. And we are so pleased to be able to welcome Maxime Gariel today. Maxime is the chief, well, I should say, till 2 weeks ago, Chief Technology Officer at Xwing, which is an aviation company on a mission to radically improve human mobility through the use of fully autonomous airplanes. And the reason I say up until 2 weeks ago is Maxime is now head of autonomy at Joby, given Joby's acquisition of Xwing. Maxime is a global expert on autonomy. He is a pilot whose lifelong dream is to make airplanes fly themselves. And prior to Xwing, Max was the principal GNC engineer at Rockwell Collins. He has a storied and creative engineering career and background, and all of the GoAERO team is thrilled to be able to welcome him to impart his wisdom to our GoAERO teams. So Max, thank you so much for taking the time, and we look forward to hearing your words of wisdom.
Thank you, Gwen. It's a pleasure to be here. You're a bit too generous on your introduction. So this morning I have prepared some slides that reflect the work that we've been doing at Xwing for the past 8 years. And the theme really is how to design your autonomy stack. And the way I prepared this was mixing together some tidbits of lesson learned and things that will be important to you as you put more and more autonomy onto the vehicle that you're designing, and also showing how we've done some of it at Xwing. So it's a mix of both. So as Gwen just said, Xwing is now part of Joby Aviation. We announced that a couple of weeks ago, and all the content that we're presenting is related to the work that was done prior to the acquisition. Very briefly about me, my life has been about making airplanes fly by themselves, starting from airliners to helicopters to small drones and back to the Caravan, and now applying all of this to the Joby aircraft. So as Gwen was saying, fulfilling the mission of bringing aviation to the masses and clean aviation to the masses. So I'm very excited to be at Joby. So first of all is, what is autonomy? For each application, you're going to have a different answer. The word autonomous is being thrown all around. So I invite you to think about, what is your definition of autonomy? What are you trying to accomplish? What problems are you solving, right? Why do you need it? How is it going to be used? Who is going to use it? And what information do you need? Being able to write clearly why you need it for and how you're going to use it, what it's called like concept of operations, are very important because it allows you to think about the use cases, the people that are going to be using it, right? If you think about the mission for GoAERO, it's about these first responders. How are they going to interact with the vehicle? How do they make sure that you keep them safe? So for Xwing, the definition of autonomy is really to change the pilot's role and location. So it's to be able to move the pilot from being on board the aircraft to being a supervisor on the ground. And the objective is to democratize aviation, reduce cost, reduce reliance on onboard pilots. And your definition, your goal of autonomy is going to be different from this one. The aircraft, in our case, needs to be self-sufficient. meaning that it is capable of conducting the entire mission, all the phases of flight, from pre-flight, taxi, takeoff, navigation, detect and avoid, including traffic that is not cooperative, and land again without the intervention of a pilot. In your case, it may be different because you may be flying shorter missions, you may be flying close to buildings, you may have to enter buildings and things like that. So that's why it's important to think about what is your definition, what you need to solve. And for us, the pilot can supervise the flight where the communication link is not required, but increases operational capabilities. So the pilot becomes kind of an air traffic controller. So the tech stack that we've done based on this definition can be applied to any aircraft. Of course, there is some level of adaptation that is required, but can manage the flight through all phases of flight. The first key piece is what we call a mission management system. It is the decision-making engine. It contains the trajectory of the aircraft and then looks at all the other subsystems on board the aircraft to decide if this trajectory is still feasible, does it need to be modified? And if it needs to be modified, how do I modify it? How do we ensure that it's safe? And also, like, what is my plan B? If I lose my engine, where do I go and land, for instance? It gets input from the second subsystem, which is the detect and avoid. Detect and avoid is a term used mostly for airborne type of encounters with other airplanes that may or may not be equipped with transponders, equipped with ADS-B. But we also use it for ground hazard avoidance. So as you navigate the airport environment, you need to avoid other airplanes, you need to avoid fuel trucks, for instance, humans that may be there, trucks, and so on and so forth. So we need to safely navigate, not only when we fly, but also on the ground. The third piece is precision navigation. As we navigate through the airspace, we use traditional methods to position ourselves, like GPS, VOR, ILS, but those are not sufficient if we need to go to all the small airports without adding a lot of infrastructure. So we are fusing vision and cameras with our GPS to increase the accuracy and integrity of the GPS, and we'll touch on that very briefly. And then you have a communication element, making sure that we can talk to the aircraft, even though it's not required. It's still need to be secure because we don't want to get hacked, be redundant, and be also within the FCC regulations. When we fly in the US and around the world, we need to comply with the rules. And finally, we have a mission control center where we host all of our pilots. And that's also like a dispatch center where pilots can hand over the aircraft to somebody else. Even though we say it's autonomous, there is still a human that is being involved, and the reason is we need to integrate into the airspace, which is very complex. We need to communicate with air traffic control. It's going to take years and years before air traffic control is completely automated, even though that's where we know it's going to go and needs to go. It will take a while. So the operator will still approve and modify the aircraft's proposed flight plan, and the operator will allow the aircraft to move to the next critical phase of flight. And eventually they'll be able to modify a number of vehicles at once. When you think about your mission, you're pretty sure you're still going to have a human. This human may be interacting with other EMS, other firefighting, or whoever is on site. They need to ensure also the safety of everybody on the scene. So this is very important to provide all the right situation awareness to this operator and all the means for this operator to prevent the aircraft from doing anything that could be dangerous. All right, so let's talk about autonomy versus feedback control. I assume that a number of you are taking or have taken in the past controls classes. So there are some controls is you make a mathematical model of your planes, of your aircraft, of whatever you're controlling. You're adding mathematical equations like a PID controller around it, where you feed that back to track a reference input. This works extremely well. You have traditional control, optimal control, robust control. And if you have a mathematical model that needs to be just good enough, it doesn't need to be perfect, that works like wonders, like autopilots, waypoint navigation. It's used for category 3 landing for autoland of aircraft. In this case, if you can write the math, don't reinvent the wheel, right? Don't try to do like some machine learning for this type of things. You're wasting your time. The math works wonders, so just do it. The next step is autonomy. This is where, in my mind, you start involving decision making. You start with a high level goal. And in our case, the high level goal was I need to go from gate 7 at airport A to gate 23 at airport B. Then you take this high level goal that you need to split into low level goals. So the first step is ensure the aircraft is healthy, start the engine, then you need to taxi, you need to select the runway, you need to taxi and select potentially the taxiway. Then you need to take off, navigate the airspace, reroute around weather. So you have like all those sub goals that keep on following one another that, and some stuff can happen in between, right? You go to taxi and suddenly the runway is closed because there's another aircraft that has a flat tire on the runway. So how do you deal with this? That's when autonomy comes into play. Like you need to replan continuously and ensure that everything that you're doing is still safe. So you have your decision-making engine that's going to generate low-level commands that will go into your automation, right? In this case is track taxiway Alpha Bravo Charlie. And this is really much some automation where you have a feedback loop. But then as you go through this, you're going to look around and detect potential hazards, potential obstacles using your sensors. You're going to need to classify those and make decision based on what you've perceived, right? And based on this, change what is your current goal and potentially what is the higher level goal, can you achieve it? So this is kind of, same structure, but quite different in nature in terms of algorithms that you're going to be using. The feedback control is going to potentially do your aviate function. So this will be making sure the aircraft is stable, that you can maintain altitude, that you are safe, even if your autonomy has to think and replan. So the time components, this is like really short, that may be running at 50, 100, 500 hertz, while your autonomy loop may be running much slower, right? Because you get more information, it's more complex algorithms. And we'll talk about that later, you may need to think about how you decouple those two things in your autonomy stack. An example of emergency planning and automation is our engine out system. So as we fly, I described, we always look at our main goal, which is to go to our destination airport, but we're always looking for what if something happens. In the case, what if we have an engine out? So this video shows real life data. We are flying, going to our destination. That fuses like all the cameras we have on board. We display some traffic that is detected around. So you see other types of aircraft. And at the bottom, so the blue line is our flight path. And at the bottom, you have a top view. We are the white arrow in the middle. And those white lines are airports that actually we see on the camera here. And the yellow is a flight path that is continuously being recomputed. If we lose the engine, this is what we're going to be following. So we're going to be doing this, do a couple of spirals, and then land. And this accounts for wind. It accounts for our altitude, manages all the subsystems in terms of flaps, in terms of propeller speed, so that we can manage our energy. So this is an example of what I would call following the trajectory engineering is like automation, but deciding which runway to use, deciding, updating the wind, updating all the systems on board is more of the autonomy level in my mind. So just an example of how that works. As I described, you're going to have to think about end-to-end mission for the autonomy. For us, it's doing ground hazard avoidance, avoiding other aircraft using LiDARs in this case. As we fly, detect and avoid, similar type of problem, but actually the sensor that you use need to be different. When you're on the ground, you only care about a few hundred meters. And when we fly, we may encounter an aircraft coming at 200 knots. We're flying 200 knots, so that's 400 knot closing speed and sometimes more. And this aircraft is going to be very small, very far away. So you need different types of sensors. LiDAR don't work in that case. So radars is a great example on top of ADS-B and transponder. We talked about the emergency landing, and the final example here is vision-based landing, increasing our position that we get from GPS with our sensors. We have flown these missions, over 500 autolands, and that's not sufficient, right? The number of time you do it in real life is just a way to show that it works repeatedly. But to really certify and bring it to market, we need to do a ton of simulation, a ton of system safety analysis. We're going to have to inject failures as we come for landing. So this is just to show that the system works well in nominal cases. And then we also have all the non-nominal cases to account for. Actually, one time we had a flat tire on landing and the system responded well. So that's the type of test you really want to, you don't want to do it on purpose, but you're happy it happened and it was well managed. All right, so as you build your team, this is going to be a multi-year effort. I expect, or I think that your teams are going to grow. You're going to lose some members, some new members will come into play. So it's really important that the initial team, the people from that start this project, think about the modularity of your code. You need to plan and architect your software from the get-go so that as you grow your team, as you, some of you will get busy for other exams and so on and so forth. So working as a team, planning for a team is very important. So build modular code where you define clear interfaces between the modules so that one team member can design kind of on their own that module, and they don't need to talk all the time and get the name of the variable and change those things with the rest of the team. So you can work more independently, you can test the modules. And by building those interfaces, that forces you to architect your system and think about what will go in each module. The next step, I'm pretty sure all of you know that, but version control, like track your software, know what version you're testing. When you run a test, a flight test or ground test, make sure you know which version of the code, so that if you have errors or if you have a bug later, you can go back and figure out like when it was introduced, has it been fixed, and so on and so forth. So good hygiene for software development, but things that take a bit of time to set and to get everybody used to will save you a ton of time in the long run. What is our modularity for aircraft? So it's not just about the code, it's also about certification with the FAA, showing that the systems have some level of independency, that the systems, we know if there's a failure, which system responds, we can mitigate those failures, we can also isolate, and we know how it propagates to the system. So for us, let's start with the emission management system, this purple box here. As I said, this is the brain of the system. So it's on board the aircraft. So all the bottom of the graph is on board the aircraft. So this is connected to each piece of each other module and manages the trajectory, makes a decision. On the bottom, the red is our vehicle management system. So this is very vehicle specific. This is going to be connected to your battery. You're going to know the state of charge of the batteries. It's going to know the health of the motors. It's going to know if you have some devices that you need to drop. It's going to know if it's attached, when to drop it, and so on and so forth. So this is really the interface between all the high-level stuff and the vehicle itself. On the left-hand side, these are going to be hazard avoidance system. So all the sensors that you add to generate situation awareness for the vehicle, LiDARs, radars, and then the algorithms that are going to manage this data, track the objects that are being detected, generate tracks so that the MMS can then modify the trajectory in response to it. And those algorithms are completely independent of the vehicle we're using on them. Then we have our sensor suite integration. This is a layer of software that is going to be interfacing those generic algorithms with the specific sensors that are on board the aircraft. So think about the driver, think about putting them into a format that can be used. So when you start today, imagine you want to buy a LiDAR. You buy a LiDAR from company A, and they have a certain protocol to use. So what we do is we take this information, we convert it into a generic format so that if we need to swap LiDAR, we only have to modify the sensor suite integration, right? This one layer. We don't have to modify this much more complex hazard detection and tracking system. Oh. What am I doing? All right. On the right-hand side, this is the autoflight system. So this is really our automation that comprises our navigation package. We'll talk about that in a second. Guidance and control, so our flight control loops. And then again, actual navigation sensor. So we have, and I could decompose that into also, the integration layer that manages the drivers, as well as which sensor you use and where you put them. The green is our communication management system. So we see that as a bunch of devices that provide a data link or a data pipe between the aircraft and the ground. So we have a router on board the aircraft that manages a number of links. Similar type of router on the ground that is going to fuse all this information and provide a single output to the ground control station where we have our operators. And the nice thing about having this is then you can also have then engineers responsible for each one of these modules, right? They know how they talk to each other, but then they can go and develop a lot of their system on their own. They can create requirements without relying on everybody else and constant interactions. All right, so we talked about the navigation. So navigation is where am I, what's around me, how do I navigate safely? I'm not sure like how far you are in your academic life, but maybe that will sound obvious. But each sensor comes in its own frame of reference, meaning that you need to know the data that comes out. How do you make sense out of it? So it could be north, east, down. It could provide body axis information like accelerometers, for instance, or no, actually, sorry. Gyroscopes. Accelerometer will be probably absolute. It could be your GPS can give you like WG84 altitude. You can have barometric altitude. In some cases, you can have pressure that could be absolute, relative. So you need to know when you select your sensor. Once I get data out, how do I make sense of it? What is the frame of reference? The first typical sensor you see on an aircraft are going to be your inertial measurement unit, IMU, that will provide you altitude rate, accelerations. And that's the basics to stabilize the aircraft. Then we add a magnetometer that can give you the heading, a magnetic heading. If you have quadcopters, that can be a very tricky sensor because it's very sensitive to magnetic disturbances. So if you have motors, this is not great. So it's a sensor that is quite tricky to integrate and have be reliable. Much easier to use on large aircraft or fixed-wing aircraft. The next one is air data. So that provides airspeed, barometric altitude, vertical speed. And one tidbit is don't forget to correct for installation. Based on where it is in the airflow, it may or may not be affected. So you may have to run some flight tests for calibration. Non-standard day, the pressure changes on a daily basis. So you need to adjust for the pressure at the location you're flying the day of your flight. So don't forget that. And all of this is really, all of those first three are like just about the aircraft. Then you have your GPS, GNSS system that allows you to know where you are in the world. We all used to it on our phones, on our cars. It has changed the world. In addition to position, it also provide timing, which a lot of other sensors use. It is great, but it's not sufficient for high precision tasks. It will not be good enough if you have to drop very precisely on, close to a building, for instance. It will work 95% of the time, but since you are interacting with people on the ground, you cannot rely just on this to safely conduct your mission. It also can be subject to bouncing, so you can have like reflections of the signal, so that can increase the errors, especially when you're in an urban canyon or close to buildings. It doesn't work indoor. It's subject to jamming, probably less of an issue for your mission in this competition, but good to know. You can improve it dramatically with RTK, real-time kinematics, that can give you centimeter level accuracy. You can subscribe to services via the internet that will do that for you, or you can create local base station. There's a number of solutions that are becoming a lot more affordable than they used to. So I highly recommend that you guys look into that. Still doesn't work indoor though. And then what is the output that you're selecting? Are you selecting WGS84 versus MSL? And know that the MSL also does not compare well to the barrel, right? You have to correct. So all small things that if you don't think about it at each step when you write your software, could bite you, because your landing site is going to be 20 feet or 10 meters in the air or underground, and that could cause a crash. So small things that need to be accounted for as you design. And you can also use it for dual antenna heading. So you have some GPS receivers that have two antennas, and that will compare the position of the two antennas and can give you a heading. So that's extremely helpful when magnetometer is not possible. And finally, here we said the GPS position will be vertical. We'll have some errors in, the GPS will give you your altitude either in WGS84 or MSL, but that doesn't tell you how far away from the terrain you are. And that's where like radar and laser altimeters come into play. And based on your mission, you may choose one or the other. Finally, all of those sensors help us navigate with the world, but don't really help if the world is changing or if you don't have a good map. So that's where more sophisticated sensors come into play, like LiDARs. So the LiDAR is going to send a bunch of lasers, build a 3D point cloud of the surroundings. It requires quite a lot of processing to be useful, because it's shooting all those lasers and they come back. So you need to know when those lasers were shot, what is the angle, what was the attitude of your aircraft, where were you, so that you can start geo-registering all of this information and build a map as you go. Now we have lots of algorithms that don't necessarily require to know your position. You can build that as you go. That's called like SLAM, simulation, location, and mapping. Lots of open source software that could be extremely helpful for this application. Then cameras, similar to, not similar, but just like LiDARs, you can use them for simulation, location, mapping. You can use one as a monocular camera, two as stereo, so that you can start building 3D applications. It requires a lot of processing if you want to do these algorithms, but now like GPUs are available in a small form factor, so this is great. And if you want to use them to detect obstacles and do classification, that requires quite a bit of training data, so that can be a bit of a challenge, right? So if you're trying to detect humans, I think it's easy because we can use other type of algorithms that are pre-trained. But if you're trying to do something very specific, it may be taking a lot of time before you can train these algorithms. And finally, last type of sensors, radars, that provide a longer range than LiDAR. So if you need to see really far, these are super helpful. Some of the issues is there will be lower resolution. So it's, there's an object, but it's really hard to know like what is the size. And there's a lot of noise. So a lot of clutter, especially if you're close to the ground. So not necessarily the easiest to work with, especially for your type of applications. And there are other sensors that was just enough to put on one slide. So for us, as we start our prime to go from point A to point B, we've looked at, it's not just like, what is the top of the line? What is the best I can do? It's like, what is good enough for the application? What is the sensor modalities that I put together so I have redundancy? But then I can certify. So we're using cameras for vision-based taxiing, for instance, to identify the lines and make sure that we know where we are on the airport. And we use also GPS, so those two things can check each other. LiDARs on the ground, cameras to detect aircraft before getting to the runway, before we land, also making sure the runway is free of obstacles. And also some cameras, infrared and radar cameras for detecting the runway. Just an example of ground hazard avoidance using LiDARs. LiDARs are kind of amazing because when you look at it as a human, it's obvious. So typically it will return those point clouds where objects are easy to see because they change the shape of the lines. But for computers, it's a lot trickier because you're getting millions of points in 3D at a time. And then what you need to do is be able to cluster. So this is what we do here. Like we're clustering all the points and then we create a bounding box and we're starting to track. And then we can do prediction to know where this is going to make sure it's not going to go where we are. We're not going to encounter it. So lots of open source algorithms to get started. The self-driving car really put that on the map. So great sensor that I would highly recommend for your applications. An example of how we've done a lot of this testing. So we have the same sensor suite on the aircraft as well on this car. But this car is a lot cheaper, a lot easier to go drive around to collect data. So we call that per se, and we drive around airports quite a bit to collect a lot of scenarios, various weather conditions. So if it rains, we're going to go out, fog, and so on and so forth. Another example is where we're fusing various types of sensors. It's vision-based, so in this case, one of the regulations, the pilot needs to see the runway before landing. We don't have a pilot on board. We don't want to downstream videos. So what we are doing is using our cameras to see the runway, identify it, and then use it to position ourselves. So in this case, this is machine learn. We're locking the runway, and then we're generating our position. So the magenta is the GPS INS localization, and then the teal is the position derived from the vision system. As you can see on this view here, so this is side view, and this is a top view. The launcher position is really good, and initially the launcher position, there's some offset because you have this long rectangle, so it's kind of hard to know where you are along, and we're using a single camera. But as we get closer, this position gets closer and closer, and that works. That's good enough for our application. So very helpful. The joy of Google Slides. All right. Another small lesson learned, as you build your stack, think about timing. When was the data measured? What is the latency between the time it was measured and the time it's used, so that you can compensate for it? Was it filtered? Sometimes you have data that is measured at 500 hertz, but you're going to sample it every once a second or like 50 times a second. Was a filter applied? Did you just take one sample? So think about all of those because that's going to impact the validity of your data. It's going to maybe cause some delays that you don't anticipate and could cause some instabilities. And the next one is validity. How long is the data valid for? Can you trust it? Has too much time elapsed? Is the sensor functioning? Did you compensate for that delay? So for each piece of data, knowing time of applicability and validity are critical so that you don't use data that is invalid and could cause failures. Typically, you would see that on a cockpit of aircraft, you can have a big red X if the data is not valid. So we don't want to rely and use data that is not valid. To make sure that you have ways, maybe it's a continuous built-in test on your sensors or on the sensors to kind of monitor the sensor and make sure that the data is correct and valid. Next step is your OS. For the flight controls, at least for that portion, it's important to use a real-time operating system because you're going to be sequencing a lot of mathematical operations and a lot of tasks, and you need to know in which order they happen. Some tasks are critical, right? Your inner loops for stabilization. You need to minimize the time between you sense your altitude and your rate to when you actuate, so that you can have the best stability, because any delay is going to cause instability. So putting this loop at a higher priority. But also, as you have different, if you start using multi-core type of processors and you're running various processes at the same time, if they're accessing the same data, is one process modifying that data, and then the second process, is reading the data that has been modified, that could cause some serious issues. So how do those processes talk with one another? How do you ensure there's data separation and there is nothing overriding it? So be careful, especially as now we're getting, I said we're getting into the certified world. We're starting to get multi-core processors. I know it's been many years in the rest of the world, but that's something to be careful of. It's easy in Python or like on the desktop to multi-thread, but how do you, when it's safety critical embedded, that can be very dangerous. So I'm not saying not to do it. I'm saying be careful on how you sequence it and ensuring that the data that you're using is the data that you want to use. And then for less time critical data, so more for the autonomy, for the algorithms that can take a bit more time, ROS2 are great starting points to communicate, while for the other, I will advocate having like direct communication. But some of the questions to ask yourself is, how do you deal with algorithms that take more time to return a solution? You may have path planning algorithms that could take half a second to 3 seconds to generate a solution. What do you do while you're waiting, right? That's also like, you need to always have a solution so that the aircraft doesn't do anything stupid while you're waiting. How do you guarantee that actually it's going to stop in 3 seconds? Do you have a way to terminate these algorithms and so on and so forth? So think about, as you bring autonomy and more complex algorithms, how much time it takes to run, how do you terminate, how do you guarantee that you're going to have a solution? And if you have algorithms that don't necessarily give a solution, what is your backup plan? So think about all of this. And finally, flight test. Flying often is good, extremely useful, but it takes a lot of time, a lot of preparation. So you need to make sure that you get the most of every second of flight. If you fly and you have a failure, which will happen, right? Failure is part of the game, especially if you have to move fast. But it will set you back quite a bit if you don't learn from your mistakes. So having logging at each step of the algorithms, logging the raw data that come out of the sensors, logging the data like at each step of your algorithm. So you can go back and figure out where the problem was. Was it like a sensor that didn't run properly? Was it like the output of an algorithm that wasn't correct? And then you can replay this data to improve your algorithms. So you don't have to go fly again, right? You can replay the same sensor output and see how the new algorithms gets better, like with the various iterations. Invest in tools for data analysis. You're going to have to analyze a lot of data, process it many, many times. So spend some time to build some good tools that you can reuse and automate a lot of that work. Building tests for the failures that you've discovered, all the primes that you've seen, use CI/CD, continuous integration, continuous deployment. So methods to run, test as you generate code to make sure you don't introduce new errors. Automate. Take your time. Use a build-up approach for your flight tests. So take off, try a feature, land, analyze the data. Even if everything was good, right? Go back, analyze the data, make sure that there's nothing that you didn't see that happened in the data that you could have missed. And then go and fly again, right? Be very progressive. Like crashing your aircraft is going to take a lot of time. It's going to be probably very demoralizing. So take your time, look at the data, assess the risk also. I know it's exciting, but if you work really hard and the team is exhausted, it's like midnight, 2 a.m. It's probably better like everybody goes home, takes some sleep, and then do your flight test the next day when everybody can, pay closer attention to the flight, has had time to think about what could happen, things that, in their sleep, they thought like, oh, I forgot this thing, or I forgot this. So don't rush. And finally, be safe. And this is all I have for today. Thank you.
Thank you so much, Max. As a reminder to everyone, please utilize the Q&A function in the Zoom to be able to pose your questions. So we have a few that have come in so far. Which have you found to be more precise in different weather conditions, a radar altimeter or a laser altimeter?
So we've used actually a combination of both. The laser gives you just a single, it's a single beam. So it works well if your surface is flat, while the radar has a much wider beam. So we've seen a better accuracy with the altimeter, but we see that we more often get returns that don't make sense, right? So we need to do more filtering on the laser than the radar. The radar is more consistent, but close to the ground, the error is a bit bigger. And again, to manage this, what you do is you build a complementary filter so that you have your LiDAR or your radar altimeter, and then you fuse that with your vertical speed so that if you lose your sensor of your measurements, you can kind of propagate what you're doing. And that assumes that the ground is flat, right? It's an assumption that can be good or bad.
Someone says, thank you very much. Is there a specific RTOS that you recommend?
I would recommend for a lot of this work actually to use off-the-shelf open source components. A lot of those, come with some basic RTOS that I don't remember the names. It's been a while. Yeah, I forgot to put that into my slide. Like there's so much nowadays that is open source. The PixHawk, the AutoPilot. Those are great places to get started. That will save you a ton of time. So if you don't have to reinvent the wheels, don't. So yeah, start with that. But otherwise, it's not my area of expertise, the RTOS, so I cannot suggest one or the other.
So speaking of off-the-shelf solutions that you were just talking about, are there off-the-shelf solutions for autonomy that we can utilize?
No. there are some, well, like ROS is a great place to get started. So the robotic operating system, so that you can start building your autonomy, all your modules, and they can talk to each other. There's this common language that they share where they pass messages, and that allows you to connect all those components very easily. So this is a great starting point. Then there's a lot of open source algorithms, papers that you can read and re-implement for, how to use LiDAR, how to use cameras to detect objects. You have pre-trained neural network to detect humans, for instance. So yeah, go online, find those open source projects and leverage as much as possible. There's a lot of really good stuff nowadays that is available.
So then speaking of that, are there sensor processing codes available in open source?
Yes. It's been a while, to be honest, but I'm pretty sure that you can find. I mean, it's kind of amazing over the past. Well, I was doing my PhD back in like 2006, 2010. There was not much code available online. There was some, obviously, but not as much. Nowadays, like every grad student publishes their code at the same time as they publish their dissertation. So there's just so much available. So do a search and leverage all of this.
Are there any types of safe flight that initially minimize an automation stack?
Yes. So first, I didn't talk too much about this. A lot of it you try to do in simulation, right? Before you go fly for real, run simulations of your vehicles, simulations of your stack. You can start building just pure software in the loop. Then you can integrate the hardware in the loop. So the software stack runs on the target hardware, and that's connected to your computer so that you exercise on the hardware. And then you'll build up for your flights, right? For takeoff, you can tether the aircraft so that it doesn't flip over. You can put, baby wheels so it doesn't tip over, and you start very slowly by just like, all right, we're gonna like ramp up and go to 1 centimeter, and then we stop, right? Just like very, very slowly to make sure that you don't go too far and too fast. So there's never like too small of a step. An example that we did for our Autoland when we started testing it. So we had a safety part on board, which helps a lot. But what we did is we generate like a runway in the sky at like 5,000 feet, and we came in for approach. We simulated the ground. So we simulated actually our radar altimeter. We simulated our LiDAR laser altimeter. And we looked at all the sequence for our state machine, making sure we go through all the phases of flight that we flared. We flared, and then, of course, we went through this virtual runway because it was not real. We did that a number of times, looking at the data after the flight. And when we had confidence that all the state machines, all the processing of the altimeter, everything was good, we could track the airspeed, track the vertical speed as desired. We came in for approach. So the first time we came in for approach, disconnected the flight at 500 feet, 400, 300, 200, 100, 50, 40, 20, 10. And, even though you have high confidence, it gets everybody into a better cycle to try very slowly, like so that to make sure we didn't miss anything throughout the flight. So don't go for the full mission right away. Go step by step, even if it takes more time.
What is easier in your mind, implementing 5-level autopilots in cars or aircrafts? Is it possible that full autopilot is easier to implement in an air environment?
Yeah, I think the problem is easier to solve for aircraft than for self-driving cars. Well, I live in a city where I see self-driving cars on a daily basis now, right? We hear Waymo all the time, everywhere, so it's a solved problem. But it took a lot of time. It takes a lot of processing, and they have to deal with so many crazy things, right? You have like crazy people, you have so many pedestrians, all those combinations. When we fly, the airspace most of the time is a lot less congested. But what becomes difficult is to perceive things really far away. As I mentioned, detecting an aircraft miles and miles away is very difficult, takes a lot of energy and takes big radars. So that makes it difficult to get to a scale that is acceptable for small vehicles, right? Some of the challenges that we're going to have for eVTOLs is putting sensors that don't take too much energy, that don't take too much real estate, are not too heavy to put on those aircraft. So I think the problem is easier to solve on board the aircraft, but certifying it is the hardest part, right? Self-driving cars, they can get away, and they're getting away without a ton of oversight. On when we fly, we are subject to regulations. We are subject to certification. We have to demonstrate that we've thought about absolutely everything that could go wrong, that we have redundancy, and for good reasons, right? If something goes wrong, we cannot pull over, right? It's the end for us. And everybody expects a much higher level of safety from flight than from driving. So that's what makes, actually, I think it's a technologically, it's an easier problem to solve, but showing that it works absolutely all the time and certifying it, it's much more difficult for aircraft than for cars.
Is it possible to carry over the ROS draft implementation easily to the RTOS certified production system?
We are re-implementing all of the communication system for the certified version. But again, right, you remember like the slide that I showed that had, you know, the red box and the yellow box, and I had this sensor integration layer, and this includes how you communicate, so ROS and the message passing. So if you make sure that you don't have ROS throughout your code, that you have, you know, your ROS layer that does the communication, and then you go into a structure that is independent of ROS for all the algorithms, then later it's easier to swap, right? ROS makes things very, very easy. So it's very convenient to go and get started. But if you plan on certifying at some point, make sure that you only use it for communication. You don't use it for other types of convenience. So it's, you know, it's taking a bit more time at the beginning, but it's a long-term investment.
The sensor suite that you mentioned, Max, is looks a little bit expensive. Are there other affordable places to get started?
Yes, so you're right. A lot of it is fairly expensive. The open source, you can go online and look at the Arduino pilot. There is a lot for everything. There's flight controls that's much more affordable. I was looking at it like it's a few $1,000s, which is still expensive, right? But the realm of things for aviation, it's pretty cheap. LiDARs are coming down in cost dramatically. So again, it's a matter of looking at how much performance do you need, right? Like the older LiDARs don't have as many points, but that might be sufficient for application, and those will cost low thousands of dollars, which is, don't get me wrong, still expensive, but it's much better than it was 10 years ago, where it was like 50, 100,000. So what I would advise is look at what you can get in terms of, don't say go for the best sensor. Go for what you think is good enough. So do a bit of analysis on paper that if I get this sensor, here are how many lasers I have. How do I manage it? Like, what size of object can I see? What is the distance I can see? Do I need to have the greatest LiDAR that can see 400 meters? Probably not. Is 50 meters enough? I don't know, but if that's the case, that reduces the price quite a bit. And then you can look at ways to mitigate it, right? The LiDAR, if the LiDAR is static, then you're also always going to see the same point. But if you start like rotating the LiDAR, then it's you can have a much better picture. So those are ways to manage to get a lower price sensor to give you a lot more data at a cheaper price.
How important do you think dynamical model accuracy is for simulated testing?
So it depends on what you're trying to test, right? And I think that's a very important point. If you're trying to test your controllers, you need about 30%. You need to be within 70% of your model, and that's usually good enough when you get to flight. If you're talking about your path planning, about other algorithms, you don't really need to have a really good model of your aircraft. What matters is like, what does your trajectory look like? Can I replan in time? So based on what you're trying to simulate, you may have different requirements in terms of performance and accuracy of your model. For flight controls, that's where you need the highest model. But for more navigation type of algorithms, you don't need a really high precision model for your dynamics.
So we're just close to time, so we'll try and get in just a few more questions, Max, if you happen to have some time. We have a couple more coming through. Let's see. For detect and avoid task, especially during flight, is the camera's detect and avoid function good enough? Especially when the object moves very fast, will it be too late to handle it and cause a collision? Which sensors play more important roles for detect and avoid during flight?
Yeah, so we have looked at cameras to detect an aircraft at a distance required to safely avoid it and maintain a separation distance of about 2,500 feet. The amount of pixels that you have to process, because again, it's kind of like it's not just ahead of you, right? You have to look almost like all around you. This is way too many pixels to process realistically. So we've decided not to use cameras for airborne detect and avoid. So the radar is a great sensor to see airplanes pretty far away, the one that are not equipped. And then we're also using ADS-B and transponder for the aircraft that are equipped. So mostly a mix of ADS-B transponder for cooperative traffic, so aircraft that have the systems, and radars for aircraft that do not have the systems.
We'll try to take one more question. Are there any unique requirements for autonomy for VTOL aircraft missions?
That goes back to the very first thing I was describing, like what is autonomy and what are your concept of operations? The answer is yes. The mission that you're trying to carry is different from an eVTOL than from a fixed wing aircraft that has to go from airport to airport. An example is going to be the off-site landing. If you lose propulsion and you have to make an emergency landing, how do you pick where you're going to land, right? If you're flying over a city, how do you choose an appropriate landing site. You don't have runways around. You don't have a lot of time. So that might be a good example. The type of weather patterns also that we're gonna see. If we have to go land behind building on top of buildings, the weather patterns, the winds are very different from what we see at airports. So those will be unique challenges for eVTOLs.
Okay, thank you so much for your time, Max. The presentation was exceptional. As a reminder to all of our participants, you can find the recording available within the next few days. It will be posted on HeroX.com. We encourage all of you, if you have not registered yet, please complete your registration at HeroX.com/GoAERO. And thank you so much once again. We look forward to sharing more upcoming expert lectures with you. Thanks very much, Max.
Thank you for having me. Bye.
Sure.